Sonnenschein.
Thank you, Nathan. Indeed, yesterday in this program, Ask the Theorist, Shiraz Minwala pointed out that there are in fact very few talks about strings in this string meeting. So I'm very happy to chair a session where the topic is a string, and I'm even more happy to have to introduce Ofer Aharony from the Weizmann Institute, who will tell us about effective strings. So, Ofer.
Thanks. So I'd like to start by thanking the organizers for all the hard work that they did in putting this conference together in these difficult times. And indeed, people often ask why strings conferences have so few talks that are actually about strings, and this talk will try to fix that. I mean, so this talk will be all about strings, and in particular, it will be about strings of the type that appear in the real world. I mean, so just like these strings that hold up this beautiful bridge in Sao Paulo, although of course I'll focus on somewhat smaller strings so that the quantum effects will be more interesting. So strings appear in many different places in physics and in nature, and we have many different types of strings. We can have solitonic strings. There are classical solutions, one of the famous ones being the string in the 3+1 dimensional abelian Higgs model. We can have confining strings in many non-abelian gauge theories in 2, 3, or 4 space-time dimensions, and also in abelian gauge theories in 2 or 3 space-time dimensions. We can have domain walls in 2+1 dimensional theories that behave like dynamical strings. We can have cosmic strings that fill the whole universe. And of course, last but not least, we could also have fundamental strings in string theory, from which we build string perturbation theory. And these categories are not mutually exclusive. As I'll remind you later, confining strings can in some cases also be fundamental strings. Domain walls and cosmic strings can be solitonic strings, and so on. So we have all these different types of strings in physics. And in this talk, my main topic will be the universal features that are shared by all of these many different types of strings. And these universal features are captured by what I'll call the long string effective action, which captures the low energy fluctuations of long strings. So in this talk, I will only discuss the stable strings that have some finite tension T. So as an example, you can consider confining strings in the Yang-Mills theories. If we don't have any dynamical quarks in the fundamental representation, then these strings are stable. And so that will be a typical example that I'll discuss. And generally, for strings to be stable, they need to be charged under some one-form symmetry. And so that will be the typical case. For instance, in the abelian Higgs model, the string is charged under a continuous one-form symmetry, while confining strings in Yang-Mills theories are usually charged under some discrete one-form symmetries that guarantee their stability. Now, as I said, I'll focus on the universal aspects of these strings, which arise when they're long and close to being straight, in the sense that the radius of curvature of the worldsheet should be much larger than the string scale, which is set by the scale of the string tension. And this effective theory is called the effective string theory, or the long string effective action. Now, this topic has a very long history, and I won't have time here to give references to all the papers I listed here. So references to developments before 2013 can be found in this review paper that I wrote then with Zohar Komorgotsky, and I listed here some of the names of the main contributors in those times, and I will try to give explicit reference to later developments. So let's start with the simplest case. Let's consider that we just have some straight infinite string in some d-dimensional quantum field theory. Again, it could be a solitonic string, a confining string, or any other type of string. And this string and this configuration breaks the Poincare group to a product of the two-dimensional Poincare group times the SOD-2 rotation in the transverse directions around the string. So many different generators of the Poincare group are spontaneously broken in this type of configuration. And you may expect to have many different Nabu-Goldstone bosons, but it turns out, as is often the case when there are space-time symmetries, that many of these Nabu-Goldstone bosons are not independent of each other. And in fact, it turns out that there are only d-2 Nabu-Goldstone bosons in this configuration, so only d-2 massless fields along the string worldsheet, which can be thought of as the Nabu-Goldstone bosons corresponding to the translation symmetries in the transverse directions that are broken by the position of the string. Namely, if you consider fluctuations of these Nabu-Goldstone bosons, then they just describe fluctuations of the string in the transverse direction. So these massless modes are always there for any long string. And generically, unless the string breaks any extra symmetries, these would be the only massless fields on the worldsheet. And we expect all other fields, if we don't have any other scale in the theory, we expect all of them to have scales of the order of the scale set by the string tension. And in particular, if we have some solitonic string, we expect the width of the string also to be at this scale. And so also the masses of any internal excitations of the world sheets should also be at this scale. Now, in many interesting cases, such as confining Young-Mills theory, the bulk theory has some mass gap, M gap. And then if we consider the full low energy effective action in the presence of a string below the scales of the bulk mass gap and also below the scale of the string tension, then really the only light fields in that case are these D-2 massless Nabu-Goldstone bosons. So in this case, we should have a low energy effective action that contains only those fields and which is completely consistent and unitary by itself. So in this context, the effective action only contains those fields. It's analogous to the Carroll-Lagrangian when the pions are the only massless fields. And as usual, it has some derivative expansion. And what we'll argue is that the first few terms in this expansion are universal. Now, how do we describe this effective action? So it's natural to choose some coordinates along the string world sheet. So I'll choose some coordinates sigma along the string world sheet. And then one way to describe this effective action is to use the embedding of the string into our d-dimensional spacetime. So we can describe by x mu sigma the position of the point sigma along the string, and that provides the embedding of the string into spacetime. And then we should write down some effective action in terms of this embedding. Now, we have no preferred choice of coordinates on the string world sheet, so this action should have diffeomorphism invariance in the sigma variables. And if we have a relativistic field theory, we should have Poincare invariance in the x mu variables. So that would be a global symmetry of this theory. Now, of course, the theory as written here could describe any configuration of the string, but we expect it to be valid only in long string configurations whose curvature is small, as I mentioned. Now, what can we do with this long string effective action? So there are various interesting observables that we can compute for it. One example is that we can consider the low energy scattering of Nabu-Goldstone bosons. So we can take a long string, scatter Nabu-Goldstone bosons from the two sides of the string, and we can compute their scattering amplitude at low energies using this long string effective action. And as I'll discuss later, we can also use the S-matrix bootstrap to constrain that. Another interesting observable that we can compute from the effective action is the energy levels of long strings. So in some cases, we can just constrain a string to have a large length L. For instance, we can consider an open string stretched between D branes. This arises in confining gauge theories. If you have two Wilson lines, then the string stretched between them is some open string of length L. Or we can consider our spacetime to have some large circle and consider a string wrapped on a circle, and then it would also have a naturally long length L. So in those cases, we can expand the energy levels of all the states of that string in a Taylor series in 1 over the length. So the leading term, of course, is just the classical energy of that string, the tension times the length. And then we have a Taylor expansion in 1 over TL squared. So there's a term order 1 over L and various higher order terms. And in principle, given the effective action on the long string, we can compute all these energy levels order by order in this expansion. And what I'll argue is that the first 4 terms in this expansion are all completely universal, independent of the properties of what the string is made of, and only higher order terms are non-universal. So they come from various Wilson coefficients of this effective string action. In particular, if we consider an open string, say between 2 Wilson lines, then the ground state energy of that corresponds to the potential between an external quark and an anti-quark in confining theories. So that's one type of observable we can compute using this effective string theory. And the nice thing about these energy levels is that they're easy to compute in lattice simulations of various strongly interacting theories. So we can match the energy levels that we can compute from this effective string action, say, to lattice simulations of Young-Mills theory, and in this way test this formalism and compute the effective action. In the next few minutes, I'll describe 3 different ways in which we can analyze this long string effective action. Depending on how we treat the diffeomorphism symmetries, I'll first discuss what happens if we don't gauge fix the symmetry. Then I'll describe what's called the static gauge, and I'll end up with a discussion of the orthogonal gauge. So at the classical level, we don't have to gauge fix. We can just work with the full ungauge fixed action. And then we need to look for actions we can write down, which will be diffeomorphism invariant in the sigma A variables, and which will have Poincare invariance in the x mu variables. So we want to write down the most general action that has these properties. And it turns out that in the context of the derivative expansion, well, in general, it's natural to write these actions using various geometric properties of the embedding of the string into spacetime. And in the context of the derivative expansion, it's actually enough to use just 2 of these geometric properties. One obvious one is the induced metric, dAx mu dBx mu, which is the metric induced on the string world sheet from the spacetime flat metric. So this is a natural object, and we can construct the intrinsic curvature RAB, which is made from this induced metric. And we can also consider the extrinsic curvature, which is basically just the second derivative of these coordinates x mu. And then from that, we can construct various other geometric invariants. Now, usually when we have effective actions, we classify them just in some derivative expansions. However, in the case of this long string effective action, that already the ground state of a long string has some non-zero derivatives. So if the string is stretched in the x1 direction, then the derivative of x1 is non-zero. So that's actually not the natural expansion in this case, but rather it turns out that it's natural to classify the terms in the effective action by what we call the weight. So we assign to any first derivative of x, we assign to it weight 0. Of course, x's always appear with some number of derivatives because the action is translationally invariant in x. So all the terms will have at least one derivative acting on every x. And then we assign to dx weight 0, and we assign an additional weight 1 to any extra derivative that acts on that. So d squared x would have weight 1, for instance. So in this classification, the induced metric on the worldsheet has weight 0, while the extrinsic curvature has weight equal to 1. And then we can classify what are all the terms we can write down with a given weight in this effective action. So starting from weight 0, there we can only use the metric on the worldsheet with no extra derivatives to construct invariant terms. And it's easy to see that there's only one diffeomorphism invariant term that can be written down with weight 0, which is nothing but the Nabu-Goto action, which is just the area, the induced area of the string worldsheet. And as I said, I'll assume that the string has non-zero tension, such that this will provide for us the leading term in a good derivative expansion. So this action has as a solution flat strings, but of course it has also many other solutions. And the leading order equations that follow from this leading order action are just that box of x mu vanishes. So this will always be the leading order term in any effective string action. Now, at weight 2, we can have two extra derivatives on top of that, and it turns out that there are two independent terms that one can write down. One of them is just square root h times r, namely just the Einstein-Hilbert term in 1 + 1 dimensions using the induced metric, and the other term is this extrinsic curvature squared. Now, as is well known, in 1 + 1 dimensions, the first term is just a topological invariant, so the fluctuations of the string do not affect it at all, so that will not play any role in the long string effective action. The second term is often called the rigidity terms, but it turns out that this term is actually proportional to the leading order equations of motion, box x mu equals to 0. So we can always eliminate it by a field redefinition and shift it to be a higher order term in the effective action. So it turns out that in this case, because of the special properties of 1 + 1 dimensional gravity, there are actually no non-trivial terms appearing at the leading order w equals 2, unlike most effective actions for Nabu-Goto bosons. And the non-trivial corrections only start at order w equals 4. So at that order, w equals 4, we can write down various terms. For instance, we can have the curvature squared or k to the 4th. It turns out that in 4 space-time dimensions or higher, we have two independent terms that we can write down that can be written in this schematic way. While in 3 dimensions, these two terms are proportional to each other, so that there's only one independent coefficient. And of course, as we then go to higher and higher orders, we have more and more coefficients as we go to higher orders. So this is just a classical analysis of the possible allowed terms. We know that if we want to analyze the theory quantum mechanically, we do have to do some gauge fix and various other gauge fixing and various other procedures. So the first question I want to ask is, does this remain true also quantum mechanically? Is it still true that the leading order corrections vanish? So to do that, I'll analyze two possible gauge fixings, and I'll start with what's called the static gauge. So if we have a long string, which is mostly stretched along the time and x1 directions, then it's natural to gauge fix to the two worldsheet coordinates to just be equal to x0 and x1. And this is what's called the static gauge. And so in this gauge, x1 and x0 become trivial, and the only remaining degrees of freedom are the d-2 transverse fluctuations of the string, these xi of sigma, which are just the Nabu-Goto bosons. So in this gauge, there's no remaining gauge freedom. We completely fix the diffeomorphism symmetry, and there's also no non-trivial Jacobian. So we write down an effective action just for these physical fields. So this is analogous to a unitarity gauge, where we only have the physical fields. And this action should obviously be invariant under the Poincare symmetry and the global symmetry of rotating all these scalar fields. So the advantage of this formalism is that it only contains the physical fields, but the disadvantage is that Lorentz invariance is not manifest in this gauge choice. In fact, it's non-linearly realized. So we have to carefully check whether our effective theory is indeed invariant under the full Lorentz or Poincaré group, similar to what we have to do in light cone gauge and fundamental string theory. Now we can again classify all the allowed terms by their weight. At weight 0, in this formalism, you can write down just polynomials in these two combinations of the basic fields. And if you check which combinations are Lorentz invariant, then it turns out that again, there's just one invariant combination, which again is just the Nabu-Goto action written in this specific gauge choice where it takes this form. Now in this gauge choice, the Nabu-Goto action itself, so already the leading order term turns out to be an interacting theory. When we expand this in a power series in derivatives, we have dx to the 4th, dx to the 6th terms, and so on. So this does give us an interacting theory already at the leading order, again, analogous to the leading order terms in the Cairo-Lagrangian for pion physics. So this is the leading order term. If we go on to weight 2, then it turns out that at weight 2, so with 2 extra derivatives, there are actually no terms that we can write down that are exactly Lorentz invariant. But there is one term that we can write down whose Lorentz transformation is proportional to the equations of motion. So that's this term that I explicitly wrote down here. Now, usually, if we have terms whose variation is proportional to the equations of motion, that means that we can change the transformation order by order such that these terms will become invariant under the new transformation. So you may think that this term is allowed, but it turns out that when you try to do that, then you actually have to modify the Lorentz algebra so that the theory at the quantum level is actually not Lorentz invariant, meaning that this term is actually not allowed. And the conclusion ends up in this gauge that, again, all the allowed terms start at weight 4, just like we found in the analysis without any gauge fixing. Now, the situation when you actually do quantum computations in this gauge is actually more subtle than that, because to do any quantum computations, since this is an interacting theory in this gauge, we have to regularize. And most regularizations that we use, such as a cutoff or a zeta function, explicitly break the Lorentz symmetry. So in those cases, when we do computations, we often find that we do have to add this term to our effective action in order to balance the Lorentz breaking by the regularization. So usually you would find that you have to add this term with a very specific coefficient in order for the Lorentz symmetry to be restored. So in that context, our effective action would have a term like this, but the important thing is that it's not an arbitrary coefficient, but it's just fixed given your regularization. And in some regularizations, like dimensional regularization, it's actually not present. So the important thing is that, again, we don't have any free coefficients at this w equals 2 order, and the non-universal terms start at order w equals 4. Now, doing computations in the static gauge is conceptually straightforward. If we want, we can compute any scattering amplitudes of these Nabu-Goldstone bosons and energy levels and so on. But in practice, they turn out to be quite complicated because of all the interactions that we have here already coming from the leading order Nabu-Goto action. So for this reason, it's nice to consider also other gaugings, and in particular, another natural gauge fixing of the diffeomorphism symmetry is to go to the orthogonal gauge, in which we gauge fix the two diffeomorphisms such that the induced metric is exactly proportional to the identity matrix. So we can always do that using the two diffeomorphisms. And this is similar to conformal gauge in fundamental string theory, but of course it's not identical because in that context we have an elementary metric field on the worldsheet and we have while invariance and so on, while here we're just using diffeomorphisms and we only have this induced metric. Now this gauge choice has many advantages. One is that in this gauge choice, the leading order Nabu-Goto action turns out to be just a free action. So this is just the leading order w equals 0 term. Another advantage is that the full Poincaré symmetry here is the manifest. And a third advantage is that this gauge fixing does not completely fix the diffeomorphism symmetry, but as is famous from conformal gauge in string theory, we still have left over a conformal symmetry on our worldsheet, which means that the effective action in this gauge choice has to be conformally invariant, which gives us very strong constraints on the action. So we have all these nice advantages. Of course, the disadvantage of this gauge is that it has some non-physical degrees of freedom, and in particular, also the gauge fixing here turns out to lead to rather complicated ghosts. And the Fadeev-Popov action leads to rather complicated constraints on the physical states. So that's the price that you have to pay for all of these advantages that we have. Now, if you actually try to compute the BRST operator corresponding to this gauge fixing in the orthogonal gauge, it turns out to be very complicated. However, already 30 years ago, Polchinski and Strominger conjectured that maybe you can quantize the effective string in this gauge by just imposing Virasoro constraints on the physical states, just saying that they're annihilated by the Ln operators, just like we do for fundamental strings in the conformal gauge. Now, there's actually no direct derivation of this procedure, but if you want, you can derive it by adding some auxiliary field to our metric beyond the x mu variables. And then if you make some assumptions about how you can write down the action using that auxiliary field and integrate it out, you can show that you do get these Virasoro constraints in that formalism. And there are various consistency checks that show that this is indeed a consistent procedure to analyze the effective string action. So I'll assume this procedure in the rest of this talk. So assuming that, we have to just write down some effective action with these x mu variables that should be conformally invariant and impose these physical state conditions on top of that. So which actions can we write down? Naively, if we want to write down a conformal action just using the x mu variables, then there's nothing we can write down because any higher derivative terms that we write down, of course, would not be conformally invariant. They would not even have the right scaling dimensions. However, here we have to remember that we're trying to write down just an action that's valid for effective strings, so it should only be valid for long string configurations. And in long string configurations, there's always a non-zero value to this combination d plus x mu, d minus x mu, which has some expectation value in any long string configuration. So that means that in the effective action, we can allow also negative powers of this combination as z. And in particular, the first term you can write down of way2, which is conformally invariant, turns out to be this specific combination. So you can check that if you allow these negative powers, then this term is conformally invariant, so it can appear in the effective long string action. And on top of that, we can also write down various higher order terms. So this is a term of way2, it has two extra derivatives, and then you can have various higher order terms. And such negative powers of this z variable can arise if you integrate out various other fields on the worldsheet. So if you have some massive fields on the worldsheet and you integrate out, you naturally get effective actions of this type. So this is the general form of the effective action in this gauge. Now, as is well known, again, from conformal gauge, if we want to impose the Virasoro conditions, then that's only consistent for c equals 26, because only then the corresponding BRST operator squares to 0. Well, naively, it looks like this effective action that we're writing down has a central charge equal to d, because that's what we get just from this first term in the effective action. However, it turns out, as was found already by Polchinski and Strominger, that if you actually compute the central charge of this theory, then this beta term also contributes, even though it seems to be a higher order term. But if you actually compute the central charge, say by looking at the 2-point function in the presence and expanding around some long string configuration, then you find that this beta also contributes linearly to the central charge. And in fact, requiring that the central charge is equal to 26 exactly fixes this first term beta to be equal to d minus 26 divided by 12. And all the higher order terms do not contribute to the central charge. So just like in all the other formalisms, this leading way2 term is completely determined and universal. However, here it takes some non-zero value, which turns out to be exactly proportional to d minus 26. So in this way, the nice roll of 26 dimensions shows up in any effective string action that you would write down for any long string in nature or in other types of physics. Now, the higher order terms, of course, are not fixed, and they match with a W bigger than 4 terms in the other approaches. So to summarize the construction of the effective string actions, we have various different approaches, and all of them indicate that we have universal terms at W equals 0 and W equals 2, and then the non-universal terms start at W equals 4. So if you translate to the energy levels, then that corresponds to this very high order of 1 over L to the 7th in the energy levels of closed strings. And in the S matrix, that corresponds to S to the 4th. So all the lower order terms are completely universal and determined just by the effective action that I wrote down. And you can check that in all these different approaches, if you compute the energy levels and scattering altitudes, you get exactly the same answer. And in particular, if you compute the scattering altitude of the Nabu-Goldstone boson, then the leading order term, as is obvious from this orthogonal gauge approach, since the first term is free, then the leading order interactions come from this first term, and they're proportional to d minus 26. So if you just consider on any long string in the universe, the scattering of the Nabu-Goldstone actions, you would find the special role of 26 dimensions there. So some tests of this effective action formalism that you can do, in some cases, we can just compute the effective action of a long string. For instance, if we have a solitonic string, we can just compute it in perturbation theory. Or if we have a holographic confining string in a weakly curved background, then we can just compute it using the worldsheet action, which is weakly coupled. And of course, the effective actions that we get all agree with this general formalism. And we can also compare the energy levels of long strings that we compute from this effective action to a lot of simulations of various theories, and in particular, to simulations of confining strings in 3-dimensional and 4-dimensional Young-Mills theories. And there is indeed a precise matching with the expectations to the order with which they can be computed numerically, which these days is quite a large precision. Now, if we want to go further, so we basically said all that can be said using just the symmetries, but so far we haven't used unitarity. So one way to get extra constraints on the effective action is to use unitarity, as we heard in the first week of the conference, using the S matrix bootstrap. And this was analyzed in particular in this context in these 2 papers. So it turns out that even if you consider just the unitarity of the 2-to-2 scattering of these Navier-Goldstone bosons, then that already provides bounds on the leading non-universal coefficients of these weight 4 terms that I described. So in the 3-dimensional case, where there's only one coefficient, you can obtain a lower bound on it analytically from these considerations, while in 4 or higher dimensions, you can obtain lower bounds on it that are shown in this plot taken from this paper of Miro and Guerrier. Now, there are various generalizations of this effective string action. The generalization to open strings, which can have Neumann or Dirichlet boundary conditions, depending on the case, is straightforward, except that in that case, you can also have extra terms appearing as boundary terms in this effective action. If you have Neumann boundary conditions, like you would have, say, for massive quarks coupled to confining strings, then the leading boundary term that's allowed is just a mass term for these quarks, which is obviously allowed. And it turns out that on top of that, for either boundary condition, the leading non-universal terms that are allowed turn out to be at order 1 over L to the 4th. So that's their contribution to the energy levels in that case. And again, we can classify all of the allowed terms and match them, again, with lattice simulations of open strings. Another generalization we can do is to cases where we have additional broken symmetries, like supersymmetries. So of course, whenever we have additional broken symmetries, we would have extra massless fields on the string worldsheet, and we have to generalize the effective action to include them as well. In particular, for instance, if you consider the confining string in the n equals 1 supersymmetric Young-Mills theory, that breaks supersymmetry completely, so that has 4 Goldstinos on the worldsheet, and this effective action was considered in this paper. If you take the confining string in 2D Young-Mills theory, then in that case, we actually don't have any Navier-Goldstone bosons, but then you do have a Goldstino because it breaks supersymmetry, so there you have an effective action containing only the Goldstino. In many cases, we can also have strings that preserve part of the supersymmetry. So these are called BPS strings, and they exist, for instance, with those amounts of supersymmetry. And of course, in those cases, the whole effective action on the worldsheet is supersymmetric. Namely, we have an effective action that realizes linearly some of the supercharges and non-linearly some of the other supercharges. And in most of these cases, the full effective action has not yet been analyzed. So it would be interesting to analyze the effective action also in those cases. So I described some objects we can compute using the effective action. Let me describe also some additional ones. You can use the effective action to compute the width of long strings. So here I'm not talking about the intrinsic width of some string solution, but rather about the quantum width coming from the fluctuations of these Navier-Goldstone bosons. So if we have some open string of length L, then the fluctuations give it a width of length L of width log L, as we would measure, for instance, from the expectation value of x squared. So that we can use the effective string action to measure and compare it also to simulations. We can use the effective action to compute the expectation values of large Wilson loops for confining strings. And another very interesting application is that we can use this effective action to compute the spectrum of high spin states. Say in confining strings, these would be glue balls and mesons. And in fact, that is one of the historical origins of string theory, when people noticed that the spectrum of high spin states resembles the spectrum of rotating strings. So for open strings, if the string has a high spin, then it's naturally long, and you can use this long string effective action to control it. For closed string, it's actually more subtle, because closed strings in 3 or 4 space-time dimensions, if they rotate, then the classical solution looks like a folded string in this way, and then the effective action actually breaks down at the position of the folds. So we have to put some extra information to compute the energy levels of those strings. But if you're in 5 dimensions or higher, then you can have non-zero angular momentum in 2 different planes, and then the classical solution is non-singular. So in those circumstances, you can compute the energy levels of these rotating strings just from the effective string theory. And for instance, this is the ground state of the rotating string with angular momenta J1 and J2 as computed by Hellerman and Swanson. And again, you see the nice appearance of 26 dimensions in this computation. Of course, the long string effective action cannot be used for many other things. In particular, we obviously cannot use it to compute the spectrum of short string states, say the light mesons and glue balls in some confining gauge theory. Also, in many theories, we have a Hagedorn temperature, which we can identify by the radius of a Euclidean circle, where a string wrapped on that circle would become massless and then tachyonic, but that typically happens at a length which is of the order of the scale set by the string tension, which is beyond the range of validity of this effective string action. So these are examples of some things which we cannot use the effective string action to compute. So I'd like to use, so up to now, everything that I described was more or less rigorous. And I'd like to use the remaining 10 or so minutes to discuss some things that we can say about what happens if we try to go beyond the lower energy effective action and try to say more things about the theory living on the worldsheet theory of these various different types of strings. So generally, if we have one of these strings, it can be again a solitonic string or a confining string, then we expect that around the scale set by the string tension, there should be some various additional modes, both in the bulk and on the string worldsheet, that will also be present, say some internal fluctuations of the string. And of course, those will also couple to the Navier-Goldstone boson. So we expect our effective string action written just in terms of the Navier-Goldstone boson to break down at this scale of the square root of the string tension. However, it turns out that there are some specific types of strings where we have a limit where these strings completely decouple from the bulk fields. And in particular, this is famously the case for confining strings in large N gauge theories, where as Topf showed in the large N Topf limit, these confining strings completely decouple from all the bulk fields. And what that means is that in this decoupling limit, the 1+1 dimensional theory on the string worldsheet, including all the extra fields, so not just the Navier-Goldstone bosons, but any fields that we have living on this one-dimensional string worldsheet, should make sense at all energy scales, not just as a low energy effective action, but since it decouples from the bulk physics, this theory should be a consistent unitary theory in its own right at all energy scales. In particular, we expect that in such cases, it should also be possible to think of the worldsheet as a fundamental string, such that when we quantize it, it will give rise to the full bulk physics perturbatively in 1/n. And of course, we have various examples of that in holographic confining backgrounds, where we have some full string theory background with some fundamental string, but then these backgrounds are confining such that if we look at long string configurations of those fundamental strings, then the only light modes are the Navier-Goldstone bosons, and we recover the effective actions that I described in the first part of my talk. But we expect that in any large N gauge theory, the worldsheet theory should be well defined by itself, and perhaps also in other circumstances where the string decouples from the bulk. So we have this 1+1 dimensional worldsheet theory, which should make sense, but in general, there's no reason why this should be a weakly coupled theory. We a priori say in confining strings, we have no small parameter that would make this theory weakly coupled. It is weakly coupled, as I mentioned, in some holographic confining backgrounds, where you can have a limit where the background is weakly curved, and then the worldsheet theory is weakly coupled. But generally, we do not expect this to be the case. And also on general grounds, we do not expect this worldsheet theory to be just some bosonic string or even an NSR superstring, but it seems that we usually need some more general formalism of string theory that can incorporate also Ramon backgrounds. So for instance, perhaps the pure spinor formalism is needed in these cases. So what can we do in these circumstances where we expect to have a strongly coupled theory on the string worldsheet? So I'll describe two types of approaches that we can take to try to solve this problem. Of course, it hasn't been solved yet, but we can either try to take a bottom-up approach or a top-down approach, and I'll describe each of these in turn. So specifically, if we consider the confining strings of large N Yang-Mills theories in, say, 3 or 4 dimensions in the large N limit, then we expect to have some well-defined worldsheet theory describing them, but there's no reason why it should be weakly coupled because those theories have no small parameters. So a priori, it seems very difficult to try to imagine writing down the Lagrangian for those theories. And the best hope would be if for some reason this worldsheet theory happens to be some integrable theory. Now, I don't know of any reason why the worldsheet theory in these cases should be integrable, but quite surprisingly, it was found in these papers that these strings actually do turn out to be very well approximated by some integrable models on the string worldsheet. So if we have some integrable model on the string worldsheet, then of course we can compute the string spectrum exactly, not just in the 1/L expansion, but we can compute the energy levels and the scattering amplitudes of the Navier-Goldstone bosons exactly at all orders in 1/L. And then we can compare the results from these integrable theories to say lattice simulations of Yang-Mills theories. And these people found that these two completely different computations actually match very well, although not completely exactly, but they match to within the level of a few percent. So what they found is that for 3-dimensional confining strings, the string worldsheet theory is actually well approximated by just taking the bosonic Navier-Goldstone action. So just this action that appeared already several times in this talk. So as I mentioned, in general, this action is some interacting theory, which is not integrable. Of course, in 26 dimensions, we know that it is integrable because in the orthogonal gauge, it's equivalent to a free theory. And it turns out that also in the special case of 3 spacetime dimensions, where we just have one scalar field x, then also in that case, this theory turns out to be integrable, which means that we can exactly compute the energy levels of this theory, even down to a very small values of L, where we would expect the effective theory to break down. So we can compute these energy levels, compare them to the energy levels that we find, say, from lattice simulations of Yang-Mills theories. And it turns out that these two computations actually match very nicely. But the reason for that is still not known.
5 minutes, Ofer.
thank you, that really perfect. Now, in the four-dimensional case, again, they found that you can match the energy levels to some integral model, where the integral model in this case contains, in addition to the two Nambu-Goldstone bosons that we have in this case, it contains one extra massive worldsheet field, A of sigma, which is a pseudoscalar field, which couples to this specific combination of the Nambu-Goldstone bosons. So there's some specific parity odd combination of the Nambu-Goldstone bosons that you can write down and couple it to A. And it turns out that this theory happens to be integrable for some specific value of this coupling QA that's in front of this term. And then there's some extra parameter in this theory corresponding to the mass of this pseudoscalar field. And it turns out that for some specific mass of this field, the spectrum that you get matches the confining string spectrum of four-dimensional Yang-Mills theory very well, including in particular, you can find on the lattice modes that correspond to excitations of this pseudoscalar field. Now, as I mentioned, the reasons for this approximate integrability are not yet clear, but it raises the obvious conjecture that maybe we can somehow systematically expand the QCD string action around these integrable theories, perhaps by adding some additional fields or interactions, and it would be very interesting to understand if such an expansion makes sense or not. So that would be a bottom-up approach. We can also try to take a top-down approach to constructing the QCD string. So our expectation from holography is that the QCD string, like the strings that we found to describe other gauge theories, should have some holographic description in which the worldsheet theory should have some extra field phi of sigma that can be thought of as the radial direction of the space in which this string moves in. Now, if we have long strings, then they will naturally sit near the minimal value of this coordinate phi. And if we expand around those configurations, this field phi is massive, and we can integrate it out and reproduce the effective string action. But if conversely, we try to look at configurations at large values of this field phi, there we know that at high energies, these field theories are asymptotically free. So in that regime, we should reconstruct the free gauge theory, and in particular, the worldsheets in this, the Feynman diagrams, or the Feynman worldsheets should become just fishnet Feynman diagrams of our gauge theory, and the worldsheet actions should become topological, where the states are just described by some string bits. So the strings in that regime should just be described as some bound states of gluons. And of course, it would be very interesting to construct such an action that interpolates between these two different limits. From this point of view, the natural way to try to construct such a string action would be to start from a string dual for a free gauge theory. And at least for the case of n equals 4 super Yang-Mills theory, some versions of that string dual were suggested already in the past, and we'll have another talk about that by Matthias Gabaldia later this week. So if we can generalize these constructions for a string dual of the free pure Yang-Mills theory, then and then deform that by the gauge coupling, then that would give us a first principles construction of the QCD string action. But of course, that we don't yet know exactly how to perform that construction. Another way to construct a top-down version of the QCD string would be to start from some string theory whose holographic dual is known, and which we can deform such that in a limit we can get to the three-dimensional or four-dimensional pure Yang-Mills theory. The fact that such deformations exist, and as I'll review in a minute, shows us that the QCD string definitely can be viewed as a limit of the standard fundamental string when we just perform some deformations of it, at least if we don't encounter any phase transitions when we perform these deformations, which we don't know how to prove. As an example, we can start from the n equals 4 super Yang-Mills theory and just add masses to all the scalars and fermions. And then if we take the limit where those masses go to infinity while taking the 't Hooft coupling to 0 and keeping fixed the low energy QCD scale, which is this combination, then that limit should give us the four-dimensional QCD string. Of course, doing that in practice is very difficult because we need to first understand the precise string dual of mass deformations of n equals 4, which are very complicated backgrounds as found by Polchinski and Strassler. And then we also have to take those configurations and take this high curvature limit of g Yang-Mills squared n going to 0. But in principle, this is a well-defined question in string theory that we should be able to answer. And similarly, we can use Witten's construction of 3D Yang-Mills theory as a limit of the n equals 4 super Yang-Mills theory on a circle when we take anti-periodic boundary conditions for the fermions. So also there, we can take some limit of this construction, which gives us the three-dimensional Yang-Mills theory. So there should be some limit of this string theory that gives us the 3D QCD string. But again, the full string background describing this n equals 4 super Yang-Mills theory on a circle is a rather complicated background for which we don't have an exact worldsheet construction, and definitely we don't understand it in this limit. So that's still an open problem. So let me summarize. So in this talk, I argued that the effective action of any long string that we can find in nature or in any part of physics has several universal terms that control many of its low energy properties. And in particular, some of these terms nicely exhibit the special role of 26 dimensions. if we have large unconfining strings, then I argue that there should be some description of the worldsheet at all energy scales, not just in this lower energy effective action, but this is yet to be found. And it's interesting to ask whether there are also any other examples of, say, non-confining strings where there would be some similar limit where they decouple from the bulk and where we would have an all-scale description of the string worldsheet. It's also interesting to ask, can we learn from other cases where we do understand the full string theory dual of some gauge theories in cases where the worldsheet action is topological? So for instance, we do understand that for 2D QCD or for the string dual of Chern-Simons theory. So in those cases, the worldsheet theory is topological, but we do understand the precise matching from the gauge theory to the string theory. So maybe these cases can also be used to teach us about the full worldsheet action for these confining strings. So there are many interesting open questions, and we'll have some more discussion of those in a few hours, led by Dubovsky and Klebanov. And I should emphasize that most of that discussion will be before the football game, before Spain and Croatia. So also football fans are welcome to attend the discussion. So thank you all for listening.
Thank you very much, Ofer. And now we have 10 minutes for questions. Please go ahead. Who wants to ask? Please raise your hand.
So I see that she raised his hand. So
okay, so go ahead.
Hi, Ofer. So I have a couple of questions. First is the one raised in the chat. So about the Deco3 string, where if you assume integrability, when you say you can determine the spectrum for all, I assume you mean the string wrapped around the circle. That's compacted back.
Right.
But if you just consider a short string, is there any way to argue that you can get the exact result, or is that supposed to be determined by integrability?
Yes, I think if you assume that that is the full string worldsheet action, then I think then you can quantize that for a string of any length. And yes, so I think that with that, of course, we know that that assumption is not true. I mean, we know that that is not the correct description at short scales. But if you assume that, I think you can try to.
What I'm worried about is that usually the integrability is about the asymptotic asymmetrics of the ensemble goes on both downs. Now, if you have the folding point of the spinning string in 2 + 1D, is that really determined by this integrability assumption? Is there some freedom there?
Right. Yeah. So that is a good question. So I'm not sure if this integral model can really deal also with this case of folded strings. I mean, maybe Sergey can answer if he's thought about that. So yeah, that's a good question. Yeah. So I'm not sure.
Right. That's why I was asking, because it's not intuitively not obvious to me that the short string spectrum can be determined by that assumption.
Right. Yeah. No. So I agree. Yes.
So another question about the confining string is that is there any no-go result that the holographic confining background has to have R flux?
Yeah, that's a good question. I think there almost is. I mean, so in flat space, there is this famous theorem by Kutasov and Seiberg that if you have a string theory with no tachyons, then it has to have degeneracy between bosons and fermions. So if you're looking at the QCD string, which doesn't have that degeneracy, then of course you cannot have just a bosonic string, and that theorem holds also for NSR strings. Now that theorem, it was proven in the case of flat space, if you have, say, R4 cross something, but I think, although it hasn't been done rigorously, I think you can generalize it also to warped backgrounds, like confining string backgrounds. So I believe that one can prove that the standard bosonic and NSR formalisms cannot describe a theory that doesn't have Bose-Fermi degeneracy, but that hasn't been rigorously proven. I mean, so maybe we can leave it to the discussion to see what other people think about that, but I believe it's true, but it certainly hasn't been rigorously proven.
Thank you.
Okay, Daniel Harlow.
Hi, Ofer. I was just wondering, so you made a comment about something that's puzzled me for a long time, which was when it is that by quantizing the string, you can also sort of recover the bulk theory as well. So can you say a little bit more about that? How do you, I mean, you just said just because the string makes sense to high energies, that's enough. But is that really true? Can you
right. So of course it's not. Yeah. So sorry, I did not mean to imply that it's enough. So of course, one requirement is that the string worldsheet theory will decouple from the bulk and will be valid at all energy scales. But the other requirement, of course, is that you should have some decoupling limit with which to set up string perturbation theory. So you should have. I mean, so as we know, in these contexts, I mean, you do have within the worldsheet action, you do have some parameter that controls string perturbation theory, and there has to be some limit of your theory where that parameter is small. So in large and confining theories, we know that the parameter would be 1 over n, so such a limit does exist. But in general, I think you need these two requirements, that you have an action that's valid at all energies, and you can take a limit where the coupling constant between different strings that governs the genus expansion goes to 0. So if that's true, I believe it should be possible to set up string perturbation theory.
Okay, Rajesh.
Hi, Ofer. Thanks for a wonderful talk. So my question was about these, when d is not equal to 26, when you're away, when you have this additional term that you wrote with inverse power z, is there some sense in which this and these terms which contribute the 26 minus d to the central charge, is there a sense in which they can be understood as some effectively a Liouville-like mode or something like that?
Well, I think the answer is yes and no. I mean, so you can always introduce a Liouville mode to the metric, which would be this. I mean, as I said, you fix in this case the metric to be proportional to e to the phi delta v. So you can always, so that phi is some combination of the Navier-Stokes bosons, but you can serve them. But if you have also additional modes on the worldsheet, then it would be determined also by these other modes. So in general, you could imagine that you have this extra Liouville mode, and then when you integrate out, you generate this field. And that's in fact the point of view that was taken by Polczynski and Strominger in the original paper. But usually, if you consider the effective action on the string, then say for the holographic strings that you understand, you see that you have many modes on the worldsheet. I mean, not just a single mode. So there would be some combination of all these massive fields that would serve like a Liouville mode. But you also have additional modes. And in those cases, the effective action would come from integrating out all of these fields. So I'm not sure if in general there would be some special mode that plays the role of the Liouville field and which really guarantees this term. But well, okay, there is one context where that would be true, which is the point of view taken by, I think, Kellerman et al. In their paper, which is that if you do include this extra metric variable, then, or more precisely, if you consider the conformal anomaly on the string worldsheet, then in that context, there is a special role that's played by this Liouville mode. And in that context, you can view this extra term as the thing that cancels the conformal anomaly on the worldsheet. And in that context, it is natural to write it using this effective Liouville variable. So in that context, it would come from that. But in general, if you're looking at the action at higher energies, I don't think there would be any special role played by the Liouville fields. I mean, in general, you would have also many other fields on the worldsheet at the same energy scales.
So
okay,
sorry.
Node IAS.
Okay, we'll continue.
Yeah, we can continue the discussion session, of course.
Yeah.
So in your discussion of theories where the effective string action goes up to high energies, I just wondered what you'd say about the Polyakov model in 3 dimensions, where the confining scale is enormously small. So the string theory, it would seem, is valid way above the confining scale, but your criterion for weak coupling isn't satisfied.
Right. Yeah, that's an interesting example that I haven't shown much about. In that example, actually, the whole effective string action sort of breaks down in the sense that you don't start from the string tension as the leading term, but at high energies, this other rigidity term plays the main role, and it's asymptotically free, so that you can get an action that's valid at all energy scales. But yeah, I haven't really thought about whether that action can be used to define a fully consistent string theory. I mean, as you said, if there's no weak coupling parameter, then I don't have any reason to think that that would be possible. But it's it's an interesting question. I don't know.
What was the statement you made about the rigidity term?
I just mentioned that in the context of low energy effective actions, I mentioned that the rigidity terms can always be eliminated if you expand around a long string with the tension as the leading term, then that rigidity term doesn't play any role. But in what Polyakov did, I mean, he considered actually a high energy expansion of the string. And in that context, it is legitimate to keep this rigidity term. And indeed, one can write down an effective action where the full worldsheet action would just include this coupling, which is asymptotically free. So I was just clarifying a possible confusion between the appearance of the rigidity term in Polyakov's formalism and the fact that it does not appear in low energy effective string actions.
Damson.
Hi, Ofer. I wonder if there is effective action for long rotating strings with massless quarks at the end.
Yeah, that's a very good question. So I mean, if the quarks are not dynamic, if the quarks are not dynamical, and so you don't include quark loops or anything, then yes, then you can write down. Then in fact you just use the same effective string action. And you just have to add some boundary terms on top. So this is one of the generalizations that I mentioned. So for that case, we do have an effective string action. of course, in an actual theory of quarks, you would also need to take into account dynamical quarks. But if you have some limit where the quark loops are suppressed, then yes, then and in particular, that is why this effective string theory matches with high spin mesons in QCD. I mean, where we do have light quarks at the ends, and the effective string action can be used for that case. That's sort of the maybe even the most obvious place to use it. Yes.
Can I continue? Yeah, maybe I can ask you privately some more questions.
Okay, sure. Or in the discussion session, I'll be happy to discuss all these issues further.
Ofer, I would like to make a very short comment. What is missing in my eyes from your discussion is how is it related to nature? And so when, in particular, if you're talking about the confining string, then there is a lot of input that you can learn from the structure of the spectra of resonances, decay width, scattering amplitudes, and that should be an input to the construction of this effective long string theory.
Definitely.
Okay, so if there are no more questions, let's thank Ofer again. And